Good morning, class. Oh, good to see you here. There's 5 of you. I said try page 136 practice example yesterday, so we're going to look at that together. It says write a balanced molecular equation for the reaction of carbonic acid and potassium hydroxide. B, write the net ionic equation for this reaction. We will write molecular ionic and net ionic. Let me just shut the door, it's getting cold in here. It's minus 17 outside today in Alberta. So carbonic acid, H2CO3, is reacting with KOH. So you're going to need 2 KOHs there. So we'll start off with the molecular equation. What you're going to end up with is potassium carbonate and 2 waters. Now, to write the ionic equation, what really happens here is because this is a strong base and this is a weak acid, this is going to dissociate completely, and it's going to give you the water, and you're going to get the carbonate anions left over. So the net ionic for this is that the H2CO3 stays together, but it's called aqueous. The potassium hydroxide releases hydroxide ions. You get water as your final product, and the carbonate anion is remaining in solution. That's your net ionic. Now, this reaction would also produce some gas, because it would the carbonic acid would break down in the neutralization reaction. And they show that with the reaction of hydrochloric acid with sodium bicarbonate. Acid base with gas formation. If you mix HCl and sodium bicarbonate, you're going to get sodium chloride and carbonic acid. But carbonic acid is unstable. So what happens is it breaks down into water and carbon dioxide. That's why if you mix, if you were to mix any acid, say even vinegar, with sodium bicarbonate, you get a lot of gas formation. It's one of those experiments that every little kid does in the kitchen. The next thing is oxidation reduction. We cover oxidation and reduction more in depth at the end of the year, but I'll introduce it to you now because it's part of chapter 4. Board's not very good. I can feel it starting to curl. There's moisture in the air. I guess it's either moisture in the air is causing it to curl, or it's drying out and it's getting bumpy. That's what you get for $20. Oxidation and reduction is what you call coupled reactions. Whenever you have one substance giving up electrons, the other is taking the electrons. So it's basically a reaction where electrons are transferred. We can say oxidation, reduction, reactions are where electrons are transferred. Oxidation is a loss of electrons, and reduction is the gain of electrons. You could say Leo says Gur. Loss of electrons is oxidation, gain of electrons is reduction. That's how you can remember it. So when a metal corrodes, say for example when iron rusts, it loses electrons and forms cations. What does it lose electrons to? Well, whatever wants the electrons more than the iron or whatever metal is being oxidized. In the case of iron, it's usually oxygen. Oxygen is the usual suspect when you're oxidizing iron. And in fact, iron forms a complex with oxygen. It forms a compound, and you get rust. You get this brown, flaky substance, which does not have the same structural strength as the original iron, which is why we paint iron, because you don't want to expose it to the oxygen and the water and the air. And iron tends to rust especially quickly in the presence of water, because the water if it's touching the surface, very often it has oxygen dissolved in it, and it brings the oxygen right into intimate contact with the iron so that it can react. I'll show you a fairly vigorous reaction where calcium is attacked by hydrogen. No, wait a minute. Yeah, right. So, for example, if you put calcium metal with hydrochloric acid, you would get a vigorous reaction. Hydrogen gas would bubble off, and your calcium would be oxidized. It would lose 2 electrons. If you'd be kind enough to check in, that would be nice. If you expose calcium metal to oxygen, you can get a similar reaction. calcium oxide. Balance it. Okay. So let's review the oxidation numbers. These happen on page 139. And I'll do a couple of examples on how to attribute the oxidation state of different elements. Atoms in their elemental form have an oxidation state equal to 0. So for example, if you find hydrogen in its natural state, hydrogen is a diatomic element, its oxidation state in that state is 0. Oxygen in its naturally occurring form, the kind we breathe in, oxidation state equals 0, and so on. Second rule, for monatomic ions, equals the charge. Example, if you have calcium with a +2 charge, that equals +2, the oxidation state. If you have sodium, it's +1. If you find sodium in its natural ionic state. For nonmetals, good thing to keep in mind, I've asked you this a million times in class, which metals, I just gave it up, which atoms give up their electrons more easily? Well, on the left side of the periodic table, you have the metals, right? So the metals give up electrons more easily. They're much more easily oxidized. In fact, pretty often the definition of a metal will be something that is easy to oxidize. On the other side of the periodic table, you have nonmetals, and they typically like to take electrons. They form the basis for the reaction between metals and nonmetals. And metals like to give up electrons, and nonmetals like to take them, and you get ionic compounds forming as a result of it. For oxygen, which is 21% of our atmosphere, and it's the reason why we call reactions in which you have oxidation taking place oxidation reactions, because more often than not, the thing that's taking away the electrons is the oxygen, because it constitutes 21% of our atmosphere. So, oxygen is usually -2 oxidation. It's -1 in peroxides. Hydrogen is +1 with nonmetals, and it'll be -1 with metals. So depending on what you stick hydrogen on, Hydrogen is kind of ambivalent. It goes one way or the other, depending on what you couple it with. And finally, fluorine is always -1. Nothing can oxidize fluorine. Fluorine will oxidize oxygen. That's how powerful an oxidizing agent it is. Most other halogens are also -1. Except when combined with oxygen. You combine certain halogens with oxygen, you can actually get positive oxidation states for halogens when you combine them with oxygen. So the sum of the oxidation numbers of all atoms in a neutral compound is 0, and the sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. That's the fourth rule. Erase the other ones. I'll just erase the top one. In polyatomic ions, the sum of the oxidation states equals the charge on the ion. On neutral compounds, it equals 0. We'll do a few examples and you see what I mean. So in practice exercise on page 140, it asks, what is the oxidation state of the bold-faced element in each of the following? P2O5. Since oxygen is the one that's usually the easiest to predict, we always start from the oxygen when we see it. So let's go to P2O5. This is practice example, page 140. Let's determine the oxidation state of phosphorus in P2O5. We know oxygen is almost always -2. There's 5 oxygens, so you would expect the thing to be -10, but it's 0. So that means the phosphorus has to be +10, which means each individual phosphorus atom is at +5. Because 2 times +5 equals +10. Because there's 0 charge on this ion, then the -10 has to be counterbalanced by something just as positive, and that's what's going on. I'm just going to take a sip of my coffee while you work out sodium hydride. Tell me what sodium hydride. Tell me what sodium's oxidation state is. See if you can answer in the next 1 minute while I take a sip of my coffee. Good coffee. Anybody out there? Hello? All right, here we go. Ramella, Saviwe, Internet. Yes, it's period 1 class, Saviwe. I started a bit late today because I fed the cat. So, anybody have an idea what this is going to be the charge? Pretty easy one. It's hydrogen is always, if you put hydrogen with a metal, it's going to be opposite to the metal. So hydrogen adapts itself to whatever you put it with. So if you put it with a metal, metals tend to be positive, the hydrogen is going to be negative. Okay, hi Brandon. So the hydrogen in this case is -1. And therefore the sodium is going to be +1. Okay? That was an easy one. Let's do dichromate, Cr2O7. It's got a -2 charge. Oxygen is almost always -2. So you got -2, but there's 7 of them. So you expect it to be -14, but it's only -2. So something is bringing it back up by 12. And that's got to be the chromium because it's the only other thing in the molecule. So how do you get 12 distributed between two molecules? They each have to be +6. So chromium has a +6 oxidation state, and 2 chromiums will give you +12. So the -14 and the +12 brings you back up to -2. So chromium has a +6 oxidation state in dichromate. You see, if you combine substances with oxygen, that's how you get these crazy oxidation states that are, like +6 or +5. You can even go as high as +7 with things like manganese. Let's do the next one. Stannic bromide, SnBr4. So bromine is a halogen. Halogens are usually -1. And there's 4 bromides, so you would expect the thing to have a charge -4, but instead it's neutral. That means the stannic has to be +4. It's kind of an easy one because if you memorize your polyatomic ions, you'll know that tin takes on 2 possible charges, either +2 or +4. In this case, it has +4. It's stannic. Barium oxide. Barium oxide is neutral overall. It's got a 0 charge when you have these two things together. Oxygen, you know, is -2. Did I copy the formula right? Yeah, no, I didn't. There's 2 oxygens actually. So oxygen is usually -2. So it must mean that it's peroxide because I know barium is only +2. Yeah, that's what's going on. It's a peroxide. Okay, so in this case, the oxygen is not -2. It's -1 because it's a peroxide. And the only reason I knew that is because I know that barium is a group 2 metal. So, and I know barium doesn't have a +4 charge. So -1 times 2 of them means there should be a -2, but the thing is 0 overall. So it's got to be that barium is +2. So really, I kind of worked it backwards this time because I know that barium is being group 2 has to be +2. So that told me that the oxygen had to be a peroxide because normally you would only see BaO. It would be -2 with +2. But because there were 2 oxygens, it told me that the oxygen had a -1 charge overall. Let's show you what happens when you combine oxygen with chlorine. And you can see that even though chlorine is pretty electronegative, being a nonmetal, the oxygen has a much stronger attraction for the electrons, and it can actually cause chlorine to get to some pretty high oxidation states. So let's look at the oxidation state of chloride. So for chloride, it's got a -1 charge. That's pretty easy. It's -1. If you have hypochlorite, which is -1 charge, oxygen is usually -2, but the whole thing is -1. So that means that the chlorine has a +1 oxidation state in this particular molecule. In chlorite, which is -1 still, but it has 2 oxygens, because oxygen is usually -2 and there's 2 of them, you would expect the thing to be at -4. It's actually only at -1. That tells me that the chlorine has to be at +3. In chlorate, also with a -1 charge, now there's 3 oxygen atoms, and they're each -2, and there's 3 of them, so you would expect it to be at -6, but it's only at -1, so that's going to tell you that the chlorine has to be at +5. So you see, the more oxygen atoms you pile in there, the higher the oxidation state the chlorine attains. And finally, if you look at perchlorate, perchlorate is ClO4 with a -1 charge. Each oxygen is -2. There's 4 of them, so you would expect it to be at -8, but it's only at -1 because that chlorine atom actually attains an oxidation state of +7. All right, so you can see that certain atoms, if you put them in combination with oxygen, or even fluorine for that matter, they attain some pretty high oxidation states. So just look at this marker. I bought it. I'm 3 days in. It's already almost finished. That's what you get. This is what you call fake marketing. That should have lasted a lot longer. The next section of the book talks about oxidation of metals by acids and salts. These reactions are called displacement reactions because the ion in solution is displaced or replaced through oxidation of an element. So this is what we call single displacement reactions. I've described this before, but just to check your knowledge, let's go over that. So the single displacement reactions are actually redox reactions. In a single displacement, a substance, well, we've looked at metals, but it could also be nonmetals, displaces another because it has a higher oxidation potential. You can exploit this type of single displacement reaction. You can take any metal that's oxidized, and if you combine it with another metal that has a higher oxidation potential, you can rust the other metal in reverse. So for example, if you took a piece of lithium and you put it on top of a piece of rusty iron, the rusty iron would become reduced and the lithium would oxidize. I wouldn't recommend holding it there with your hand because you'd probably burn yourself. Lithium is extremely reactive. But this is typical. You can use one metal to rust another metal in reverse as long as the metal that you're applying to the rusted metal has a higher oxidation potential. The way we can determine which one has a higher oxidation potential is by memorizing the activity series, which goes like this: lick, ba, ka, na, magal, min, oh, not magnesium, min, zinker, fecal, nisin, PBH. Notice how hydrogen, it's not exactly in the middle, but they put it in the middle. When chemists started to think about electrochemistry, they said, okay, let's give hydrogen an oxidation potential of 0, and we'll compare all the other metals to hydrogen. So hydrogen has oxidation potential of 0. If you look it up, it's listed as 0. So it goes PBH, then QAG, HUG-PTAU. You'll notice that all the metals that are at the bottom of the activity series are the least reactive ones. You see gold, you see platinum, you see silver and mercury. They're all metals that don't oxidize easily. In fact, you can use copper as a roofing material. If you did that with iron, your roof would rust to bits in a matter of a few days. You know, you'd get a leak in a few weeks for sure. And if you tried to use lithium as a roofing material, your house would catch fire. So let's just do an example to show you what it looks like. If you used magnesium and you mixed it with HCl, look at magnesium and look at where hydrogen is, because hydrogen is there. That's what's going to switch places in a single displacement is the metals or the metal-like substances, and you're going to get you're going to get MgCl, and hydrogen is going to bubble out in the form of a gas. So that's typical whenever you mix an acid with a reactive metal, you get hydrogen gas forming because the hydrogen is being reduced. The magnesium is giving its electrons to the hydrogen. What is the criterion that you use to determine whether a single displacement reaction is going to take place? Whatever you aim to be reacting has to be higher up on the activity series. So if you see magnesium is higher than hydrogen, then this reaction can take place. If on the other hand you were to reverse the situation, suppose I tried to react copper in a solution of iron sulfate. Nothing would happen. Why? Because iron is higher up on the activity series than copper, and it's already in the state of +2, right? This is an aqueous solution. Iron is already floating around in solution. It's already lost its electrons by forming this ionic compound. Copper is not going to give its electrons to iron because it's lower on the activity series. Now, if you were to switch the places, if you were to do this, if you were to put elemental iron there and you had copper sulfate, then you would get a reaction. You would get the formation of iron sulfate, and the copper would become a coating on the particles of actually what would happen is you would decolorize the solution. The copper sulfate is a blue solution. The color of the copper would disappear, and you'd get the formation of iron ions. Okay, so let me see if we can do one together. They ask us something. Cobalt-2 sulfate. Magnesium and cobalt sulfate. Okay, we can try that one. So suppose we reacted magnesium with cobalt sulfate, cobalt-2 sulfate. What would happen? Let's see. Here's cobalt. Cobalt is it higher up than magnesium? No, magnesium is higher. So yeah, in fact, it can happen. The magnesium can give electrons, because this would be the net reaction. You have magnesium with an oxidation state of 0, and you have cobalt with an oxidation state of +2. So the electrons can go that way, because obviously the thing has to be oxidized for this to reduce it. So this is going to oxidize itself, and this is going to be reduced. In the end, what you're going to have is magnesium will have a +2 charge, and the cobalt will be reduced to the elemental state. So this will have an oxidation state of 0 initially, and then at the end it'll be the cobalt that has an oxidation state of 0. Remember, loss of electrons is oxidation. So this magnesium is going to lose its electrons and become positively charged. So this is going to be oxidized. And this is going to be reduced. Okay, so that is a single displacement reaction that can go. For the single displacement reaction to take place, whatever is doing the oxidizing has to be higher up on the activity series. So magnesium is higher than cobalt, so this reaction can happen. This is page 142 practice example. And you see a picture of the activity series on page 143. I know you don't have chapter 4, don't worry about it. On page 144 of that same chapter, they ask you to answer some questions about, I'm going to leave the activity series up on the board so you can make a decision. You've done this already, so I'm hoping this is review for you. You still with me? Oh, I've lost a few. Which of the following metals will be oxidized by plumbous nitrate? So this is your reaction. You have Plumbous nitrate. And you're trying to mix it with zinc, copper, or iron. Zinc, copper, or iron. Which one of these will give electrons to the lead and reducing it to the elemental state while they themselves become oxidized? So it has to be a metal that's going to be higher up on the activity series than lead. Lead is here. Zinc is here. So yeah, zinc will work. Copper is lower, so that won't work. And iron is here, so that will work. So both zinc and iron will reduce the lead, but the copper will not. We're up to 37 minutes. I'm going to stop it there. Tomorrow, I'm going to give you some more notes about the concentrations of solutions. I still haven't written the notes, so what I'm going to do tomorrow is, well, today I'll write up the notes, and then tomorrow I'll show them to you on the screen. And then what I'd like you to do is just copy the notes out from the screen. You can pause the screen, copy the notes. I noticed yesterday, I checked, because I tried it, I held the book up to the screen, and I was able to see it very clearly on television. You can't, maybe on the phone, well, maybe your eyes are better than mine, but I was able to see it okay on the television. So that's a perfect way for me to pass the notes on to you. You'll copy them out from the screen itself, and then hopefully, you know, I don't know if the school year is ever going to resume. This quarantine looks like it's going to last a long time. I hope I'm wrong. I'd like to be able to come back by May and you know, just resume teaching so that we don't limp along like this, because this is not an ideal situation. I can't really test you properly. I'll try to figure something out, but I'm scratching my head about how I'm going to do it. If you have any suggestions, I'm open. So we'll see you tomorrow, guys. Same bat channel, same bat time. Okay. Have a good day.